My name is Carl Quinn, and this talk is building a cloud platform using Netflix OSS. And it may be in the listing for the conference. I called it "How We Built a Cloud Using Netflix OSS," but it's not quite built yet. It's a work in progress. So I sort of tweaked the name a little bit. So how we're building a cloud platform using Netflix OSS. So even though Netflix is in the name of the talk, I'm actually from Riot Games. And I'll tell you a little bit about myself, and that kind of give you an idea of why I'm doing what I'm doing and why I'm talking about what I'm talking about. So I managed the cloud tools team at Netflix for 4 years during our transition from data center-based monolithic web app to cloud-based SOA platform. And I managed the team that did the tools, the build tools, build chain, build pipeline, and the deployment tools, and how we package things and leverage the cloud a bit. But a year ago, I decided to move to Riot. It's a very exciting company. A lot of neat things are going on. And I wanted to try to take the opportunity to kind of level up my skills in cloud stuff. See if I could take all of the things I learned at Netflix and apply that same kind of cloudification architecture to a different kind of challenge, right? Much more challenging challenge. And I thought, the things I learned, it wasn't exactly as easy. I guess I knew it wasn't going to be that easy, but there's a lot of things that were kind of surprising that were not as easy to do. So I thought I would share what I learned and what worked and what didn't work in some ways with everybody else. So first I should tell you a little bit about Riot Games. I don't know how many people are familiar with our company and our game. So we were founded in 2006 for the sole purpose. I mean, the founders had one game in mind that they wanted to write, and they started working on it. And they launched League of Legends in 2009. At the time, there were about 100 employees when they launched it. So that was, basically they were a startup, like working in stealth mode for 3 years and working really hard to get the game out. And they had no idea how popular it was going to be. And so now this is, how many years later is that? That's almost 5 years later. We're 1,600 employees worldwide. We have dozens of data centers worldwide. So all over the world, we're working in different regions. We work with partners in some regions. We have our own data centers in some regions, our own offices all over the world. We localize. And so the fact that we have all those data centers is a very important asset to the company, and they're very important in the way we engage with the players. So the game that we make, just one game right now, but we are Riot Games, so someday we'll have more games. But right now we have one, and it's very popular, and we don't want to screw up the one game, so we're not really going off and writing lots of other things until we know we could do them really well. The one game is League of Legends. It's a type of game called MOBA, a multiplayer online battle arena. So here's kind of a screenshot for those who haven't seen the game. It's a little fuzzy on this monitor, but the idea is that typically you'll have teams of like 5 versus 5 that are playing in a very competitive player versus player kind of setting. So they're fighting, it's real time, using magic and kind of swords and battles and modern and fantasy sort of combined. But there's a sports-like element to it. So there's a competitive ranking and teams compete with each other. So performance of the game and latency and timing and the reliability of the game and the prohibition of cheats and things like that is very important to the underlying gameplay and the player experience. And it's something that we pay a lot of attention to. Another thing that's unique about League of Legends is the whole esports aspect of things. So we have effectively tournaments worldwide that go on at the beginning of the season, starting like right around now, and they go all the way to the fall. So here's a shot of Staples Center in LA. 13,000 people showed up to see the World Finals. And I'm sitting over there on the left, kind of back in behind the little white area. This is crazy. And the people at Staples Center thought, oh, a bunch of nerds are going to come and watch some video games, right? So it's not going to be a big deal. But this was the largest production value. We had Crystal Method did like intro music. And it was just crazy, completely full of just screaming fans all the time. And the final was between T1, Korean Telecom, and the Chinese team. And best 2 out of 3. And the Koreans just completely dominated. They dominated the whole series. And so the end was quick, two short games and it was done. But But this is an important aspect of the whole game, the environment, and the player experience is all about sports and competition and the game's integrity in that area. So here's some of our latest numbers. We have 67 million monthly active players, so people that play at least a few times a month. 27 million of them play at least once a day. And peak times, we have 7.5 million concurrent CCUs, concurrent players going on at any one time. When they first envisioned the game, they were hoping to get 20,000 concurrent players at any one time. So now we're at 7.5 million, really with the same architecture we started with 5 years ago. The same basic Java backend is supporting all of this that's going on. So we've been able to squeak out a bit more performance than we first expected. So let me first give you a little bit of context about the software platform that we've developed and how the engineering organization at Riot is sort of put together. So I came from Netflix, which worked pretty well. Teams were independent, but there was generally a very kind of a centralized coordination of ideas and architecture and design. There's like a main architect that helped educate everybody about what's the right way to use the cloud, things like that. At Riot, teams are, we kind of favor independence of teams. So teams are organized in a way that they kind of own their own destiny. So in a lot of cases, the things that we're building aren't necessarily purely technical. So to build a game feature, there's always other disciplines involved than just a bunch of coders. There are artists and animators and production people and sound people, and every piece of a feature is sort of has this little stack. So those teams are empowered to produce their feature in a way, and they can choose what they need, what technology they need to use to get things done. And so in a lot of cases, the team says, we need to use AWS in this case because we need to get this done. We can't wait for data center hardware, so we're going to create a new AWS account and just do something on our own. Tell IT to give us the credit card so we can have an account and start doing stuff because we need to get our feature done. So that's happened quite a bit at Riot. And each team uses AWS in different ways. So they've had different ways of deployment, using shell scripts or using Chef or like finding some third-party thing that they put together. So other teams are doing different things. There's not a lot of sharing in that case because they all sort of went off and now they're a little bit incompatible. So Riot Software and different teams, but for different use cases, have chosen to use different technologies to solve their problems. So the web guys, they're writing lots of JavaScript, PHP for the backend. That's how a lot of websites are built. So that's what they use. The game lobby, which is kind of where you go on the client side when you first fire up the game, is written in Adobe Air. I mean, it's a nice cross-platform. It's got a lot of good tools for artists and people putting content together. The lobby talks to a backend, which is written in Java, and that's our big enterprise Java app in the backend. That's sort of the monolithic thing that we've been able to grow and nurture into a big giant thing. And there's other game services that sort of satellite around the platform, and I actually have a diagram on the next slide. And then the game client and server themselves are written in C++. So that's sort of like down to the metal. How do you talk to the graphics engine, rendering, GPU, all that kind of stuff? That's the actual game when you're playing in the game is C++. So here's what it kind of all looks like put together. The lobby is where the user will spend a lot of their time like forming teams, checking stats, watching videos of games. It's all sort of embedded in there. Chatting with their friends, seeing who's online, and then it's like forming the game, getting the team set up for the game, which champion is everybody going to use, and getting all of the selections made that you're going to do. And then you finally say, okay, go, countdown, the game starts. The lobby spawns off the game client for you on your machine, and the platform spawns off a game server instance in the back end. And they both come up and then sync up, and you play using that one instance of the server is talking to the one instance of your client for the 10 people that are playing until the game is done, which could be up to an hour or so. So I'd like to give you a little bit of overview of how all the pieces work. So the first approach that I took trying to get people to the cloud was find all the teams that are using AWS So the website was already using AWS API, so we have like a public API that's available to third parties. That team was already using AWS, and the big data was doing quite a lot. So what we wanted to do was look at some tools, borrow what we could from Netflix, and try to standardize the build and deployment and how that was managed. So to leverage what I knew from Netflix. So phase one, let's try to get that infrastructure and tooling in place. So I grabbed a set of the Netflix tools. I don't know, how many people are familiar with the Netflix open source tools and how they work together? Okay, just a couple. Okay, so this is good. Netflix follows a model that's very unique, I think, in a lot of ways, where instead of trying to do deployment and assembly of your application and your machine at deployment time, for instance, running Chef or Puppet, trying to install packages onto the machine, they do that at build time. So during your build process, you actually are assembling a machine. Maybe you're putting your app into an RPM or some other kind of package. You know, different teams did things a little differently. But at the end, you create a base machine that everybody's going to share. So you kind of build up. You pick in a case of Linux like CentOS, add some packages to that, and take a snapshot of that base image. And then that's used as a base for every single application build. So whenever an app goes through continuous integration and you want to build and bake an application image to be ready to be deployed, you just take and drop in the RPM for the app onto that image, snapshot that, and put it out into AWS so that it can be then deployed from there. So when it's launched and auto-scaled out into a cluster of machines, it's all ready to go. So it's one machine image with app, everything's ready to boot and just start running. So there is no moving parts at deployment time. So there's a little bit of overhead in the tooling. You have to be able to do that baking step very efficiently and very fast. You have to be able to clean up the packages that, the images that you create that you never use. So you have to be able to manage those things. But once you have that tooling in place, the reliability of not having any moving parts during launch time of the machines, during deployment time, is very valuable. So Netflix has a tool called the Aminator, which they open sourced about a year ago or so, which is the tool they use to do AMI snapshotting, and we call it baking, which is mounting EBS volumes and making the snapshot. So it can be automated very easily. Asgard is the tool that they use, which is a sort of a web UI front end for basically manage. It's like an alternate AWS console. And it allows you to manage all of the different kind of AWS resources. And it also has a little bit of a workflow for doing auto-scaling groups and pushes for deployment. So they can do a rolling push or a red-black push, different ways of managing your rollouts for new deployments. And there's a few other tools, ETE, Simian Army, and ICE, which are handy sort of maintenance tools, which I can briefly go into in a little bit. So in order to use the Aminator tool at Riot, we're pretty much a chef shop at Riot. So the current deployment technology that's used in the data centers and in some of the cloud teams is to just do a standard chef deploy with chef server and everything. So we had a lot of cookbooks and a culture of trying to build and maintain libraries of cookbooks that are reusable and improving those all the time. So we wanted to leverage that library and that knowledge that we already had. So because Aminator is open source and Netflix is open to taking new plugins, we wrote a plugin for Chef for Aminator. So that's available on the Netflix site. So there's a separate repo called Aminator plugins, and there's a Chef one. Other people have contributed other plugins for Ansible and other tooling like that. So yeah, okay. And another thing that we had to do, the way we work with Nexus is we have authentication. So we have a little bit of security to prevent people from pulling binaries and things directly out of the repository. So we've had to add authentication and handling of credentials so that during baking time, we can authenticate with Nexus and pull out the packages. So that was a little bit of extra work that had to be done. So we're able to now bake base AMIs, application AMIs, and whatever distro that the teams happen to need. So right now, we're pretty much a CentOS shop. We've dabbled with Ubuntu sometimes. So it really doesn't matter much at this layer because the tooling can handle whatever we want, and it's just a matter of what the team chooses to use when they do their deployments. And there's some more recent work. So if you're looking at Aminator as a choice for doing packaging, there's also another tool called Packer from HashiCorp, which now can do AMIs. It's also able to do more virtual machine packaging like VMware and different cloud packaging, VirtualBox stuff. So it has an option now to make AMI, so that it is another alternative to look at. So what the bakery system looks like in our model is something like this, where we have artifacts that are delivered to a repository like Nexus or Artifactory, which would include things like RPMs. So those are holding the application artifacts. Then the bakery itself, we generally just run it as a Jenkins slave. So we have a Jenkins master, which is just the bakery, and we run a slave. And the slave has to run in AWS because of the way the imaging snapshotting is done. The master could be anywhere, but the slave needs to be there because it has to be an EC2 instance. So Aminator's running there, the Chef plugin is installed there, and when it's time to do a bake, an input AMI is selected for the baking operation. So in this case, you would choose, if you're going to build an application image, you start with a base OS image that you've prepared earlier. That is sort of your starting point for your applications. The Aminator mounts the volume in EBS, so it takes the snapshot, creates a mounted volume. Then it does some Chroot magic and drops into that volume and pretends that's a whole image. It basically looks at that volume as the whole machine that you're trying to make without really running it. So this is sort of the magic where it's Chrooted in there. It looks like the new machine that you're going to be creating, and it's able to install packages into that machine with a little bit of magic going on to fool the package manager into not seeing the outer machine, right? So it just thinks that's the machine. But we haven't even had to start or launch an instance to do all this work. It's just done on a volume, so it's quite efficient. And at the end of the process of all of the installing things that are happening, and all those installs happen through the plugin. So in this case, Chef plugin, but you could have an RPM plugin, you could have the Ansible plugin. That's doing the work of provisioning the bits, the packages onto the machine. At the end, Aminator picks up at the end as the last step where it snapshots that volume to create a new image, and then registers it with Amazon API so that it's now available to your deployment tools. So that whole operation can take anywhere from like 2 to 5 minutes. It can be pretty fast, depending on the load and how much stuff you're doing during your provisioning phase. But that's not so bad for creating a complete machine. So once you've got the machine, you've effectively created a completely generic application machine image for your app. So that machine image may be launched in different data centers. Well, so we're in the cloud. So it could be launched in different regions. It could be used for different purposes or for different environments, depending on where you launch it. So you need to be able to control that. So we use the tool called Asgard to do the launching and the deployment of the image. And Asgard leverages a feature of AWS, which is called user data. So AWS gives you a big chunk of data that you can pass to your instances when they launch. So you can have up to 16K of just whatever you want to be passed into the image or the instance when it starts up. And that way it can personalize itself just a little bit, right? You don't want to do too much every time there. You don't want to have too complicated of data in there, but you want to be able to tell the instances in a particular cluster when they come up that, hey, you're in this region, I want you to behave this way. So you can pass in environment variables and settings and context so that the image can personalize its configuration a little bit when it's brought up. So that when you launch, you could, for instance, launch a cluster and say, your beta test cluster, and launch another one that says, your production cluster. The same bits can be used, so you can reuse the same image you've baked and tested already to then relaunch it in a production environment and just tell it, hey, now you're prod. Okay. So we extended Asgard a little bit so that we can have more control over what goes into the user data. So out of the box, Asgard will just dump about 5 environment variables and create a shell script, which is then passed in user data. That's pretty useful, and in a lot of cases you can get by with that. I wanted something a little more powerful so that teams could adapt in how they grab that data and what they put in there. We also added and leveraged the built-in one login support for Asgard. I've started to play around with adding LDAP support and talk to Active Directory, but that was a lot of work, so we just went and used one login. It was easier to get us to migrate. So we're on the fence of already ready to go to one login, and I told the guys, hey, I would really use it if you did it. So they pushed them over the edge, and so that was easier because Asgard already had it. And we've got on our backlog so a little more fine-grained authorization work that we could do, especially as more and more teams start using the same account. It'll be interesting and probably useful to have sort of per team authorization. So teams could say, only members of my team are allowed to modify things about my application. So that's sort of a TBD. It's on the backlog also for the Netflix guys. So whoever gets to it first can write it. So here's kind of the typical flow of a deployment with Asgard with the plugin that I've created. So Asgard will take and generate user data every time you do a push. And that user data then gets put into the launch config. And so the whole auto-scaling group, all of the machines, all the instances that come up in that auto-scaling group will get that same user data and all behave the same way. And so the default, as I mentioned, is just dump in about 5 environment variables. But you can override that plugin. There's an extension point in Asgard. And you can do anything you want there. So you have a lot of context about what's happening in the deployment, what is the application, what region are we in, what stack are we in, and so all the sort of the coordinates of what we're doing, where we're doing it. So the plugin I've created is called the repo-sourced user data provider. Very typical big long Java class name. And you just configure it in the Asgard config under the plugin section. And this is actually a bunch of files all sort of mushed up together, trying to show it all in one slide. But the way I did it, it's really just a bunch of get calls. So it does get, and it does groovy string interpolation, and it does more gets and groovy interpolation so that you can have variables and indirection and build things up. But in this case, I have set up the base pointing to our GitHub repo. And I just said, we're going to put our configs into this area of GitHub. And so all we need to do is tell this plugin where the root of our GitHub area is that we're going to use for deployment configs. I have an access token here, which is sort of for authentication with GitHub, just using the standard kind of GitHub APIs. Accept what kind of data do we want, and some formula paths. So it's going to look for each application that you're deploying, it's going to first look to see if the application has a formula. And if it doesn't, it'll try to find a generic base formula and just use that. And then the formula itself, it's going to then find the first one it finds. It'll look at the formula. In this case, I'm saying it's just a YAML file that says, what is it? It's going to be shell. It has multiple parts. The first part is go grab another file from GitHub and pull that out and look at it and do string interpolation. We're going to do substitution, yes. We're going to do a copy. So it's basically just telling us how to build property files to be dropped into the directory where the app is. So in this case, the Java app is going to read application.environment.properties so that we can then build a bunch of property files up for the application and substitute. So when the app starts up, it can see where it is and all the things we want to populate in there. So some of the other tools that we've leveraged, the Simian Army is a really nice collection of monkeys. Everybody's heard of the Chaos Monkey, or maybe that's the most famous monkey of all, and it's pretty cool as an architectural guideline for how to build and architect your cloud systems, or in typical SOA, microservices kind of system, is don't make things, so what's the word? It's like your services should be stateless and resilient to failure, right? So the machines in the cloud could fail at any time, so you shouldn't rely on any one machine living forever, right? So you need high availability. You need to be able to handle something coming in and causing chaos. But actually, it turns out, I mean, that's a great thing to talk about. And when you're really mature with your SOA, you should be able to run Chaos Monkey. But I think initially, you'll probably want to look at Janitor Monkey and Conformity Monkey. So Janitor Monkey is really good at looking at all of the things that your tools have created, all of the launch configs, all of the AMIs, and kind of tell you what's sitting out there that's just junk and nobody's using, and should it clean it up for you, right? And you can configure it to, just start cleaning up. Anything that's not used, it's more than 30 days old, it can just start deleting stuff for you. So that, having Janitor Monkey working and configured will help you worry less about your bill. If you're making AMIs every hour in every region and cranking out lots and lots of storage on S3, the monkey will help you save money. And Conformity Monkey will help you also find out if you have teams that are making little one-off things and creating snowflakes that aren't following the structural rules that the Netflix tools like. So if you've created like firing up instances on their own, in the Netflix model, you always want to create instances in an auto-scaling group. Even if you don't auto-scale it, and even if the group is only one machine, putting it into an auto-scaling group lets you sort of identify it. So you can identify it by the group name, and then there's a lot of metadata that you can find out around that. What application was it, what launch config, what AMI, all of that's easier to kind of trace together in a group. Now, ETE is another interesting tool, which is kind of, so ETE is like the story or the poem of the cloud, right? So in this case, it's the story of everything that's happened that you've done in the cloud, and it creates that story by just making API calls and looking at what's out there in your account and just keeping track of what's changed between moments in time. So you can see objects were created at this time, then they went away, then this came up over here and it went away. So you can go back and use that to query and create tools. So for instance, we created a client-side scripting tool in Ruby, just made ETE API calls. It's just a REST API. It has actually no GUI or anything on it at all. But we could then scan and audit for things that weren't necessarily enforced, like what ports do you have open on your security groups? Are you following best practices for limiting the ports? Or do you just open up, teams opening things wide open and not paying attention to what they're doing? So this way you can create some ad hoc rules and structure around what you want to allow teams to do in the cloud, or at least just look and see what's going on and be aware of it. Then ICE is another interesting tool which provides visibility into the usage and accounts, by accounts and cost and resources. In the latest version that they've come out with, they've extended it a little bit so you can do tag-based rollup. So you can configure it to group resources and give you kind of roll-ups cost based on arbitrary tag values in AWS. So you can tag your resources by team and then look at cost by team if you do that. So we've done all this AWS work, and with the first projects I was working with, and that was great. So a bunch of the smaller teams that were doing AWS already were able to kind of jump over and leverage the tools that we put together, and they were very happy about that. So that just sort of leveled them up a little bit, made them a little more efficient. But public clouds, AWS in particular, and I think all of the public clouds, they don't necessarily meet the needs of all of the apps that we're trying to build. So as I mentioned before, we're in so many regions all over the country. We really care about latency to the players. So gameplay, we really need to be able to deliver game server performance down sub 50 milliseconds everywhere in the world where our players are. So even if we could get the performance out of the hardware on EC2, we just don't have the regional locality everywhere that we need to. So we still need data centers. And actually, Riot's pretty good at building new data centers. We're pretty efficient at it, and we're not afraid of it. But we do like the cloud for something, so we want to be able to leverage both. And it turns out, maybe one of the bigger problems, and this is something that it should have been obvious, but maybe it wasn't as obvious to me, is that I think maybe the biggest problem isn't moving your service to the cloud. I mean, getting your code ready, moving to the tools that are in the cloud, it's not so bad. That's pretty well documented. But if your application's not architected in a way that's sort of broken up into an SOA type model, you're going to have a lot of trouble moving it to the cloud and really leveraging it. And I suppose you could just sort of forklift the whole thing over and drop it in and then sort of fudge around and make it work, but you're really not going to get the benefit of the cloud, and it's going to be a hard sell. You're going to get over there and not see any kind of benefit, and you're just going to see a lot of the risk in the cloud there. So one of the first things we need to do is sort of cloudify the apps, make them cloud ready. People use different terminology like that, or cloud native, cloud ready. And a lot of it really is just following good principles for building a service-oriented architecture. So making things small, services independent, making them stateless wherever possible, and connecting them with a sort of a standard, in our case, REST type interface. So I think this is probably a lot of the case for companies trying to move enterprise apps to the cloud, is I think they look at all of the cloud tooling and cloud features and maybe don't think enough about what you need to do with your app architecture first. So first step, make your apps nice. So it turned out, yes, good code and good architecture, right? So and maybe, I mean, there's perfectly good cases for having big monolithic app. In our case at Riot, building the platform as one big app, leveraging big services like coherence to do caching and database and sort of shared storage, got the game built and got it going and got us up to 7.5 million concurrent users. I mean, it got us there. It's just the next step we need to move forward. And so at the same time, I was trying to do the cloud stuff, another team was trying to look at the initiative was trying to go, how are we going to take our platform to the next generation? How are we going to refactor that and break it up into services? So there was a lot of work going on there. So we joined forces. And one of the other things that came out around that time was we settled on a way, because we're so independent, with all these separate little independent teams kind of driving their own destiny, we needed a way to coordinate all the teams. And so we came up with a system which is basically RFC type system, where somebody will put out a request for comment, people will comment on it, and we get buy-in from a lot of teams, so a very cross-functional way, and we standardize on things. And so then it becomes a lot more easy to coordinate sort of shared technology across the company, at least shared specs. So we came up with the ambassador spec, which was a way to share and agree upon how to talk between services. So this is not really a giant major breakthrough. It was just getting everybody to agree on some standard stuff. We're going to use REST. We're going to send JSON in the payload, at least as least common denominator. You can do something else if you want, but you have to speak JSON at least. Error codes are done a certain way. And Swagger, which is an interesting metadata format for JSON REST, which provides a bit of metadata about your REST APIs, so you can then visualize them with debugging tools and inspection tools. And you can even use that metadata to generate code on the fly, like proxy stubs and things like that. So that was part of our spec. And we started building a library called Hermes, which was an implementation of that client server for Ambassador in Java, using Jersey and Jackson, generally setting up with Jetty server, Jetty or Netty for servers, and dynamic Swagger generation. So that became like a really good foundation for building SOA apps. And let's see. So, but we also wanted to leverage some of the Netflix architecture ideas. So these are some of the Netflix architecture in terms of how it does things at runtime. Oh, I'm out of water too. So this sort of from the picture I had before, where you deploy an app and you have a cluster of apps running. They are all launched from an AMI. They come up, and in order to find each other, they use a REST calls to a service. One service they need, so they need one address to find where the discovery service is. So they have this service called Eureka. It's a Netflix open source project. It's a discovery service. So once the app comes up, uses DNS to find one name for the discovery service. That discovery service can then give it back the addresses of everybody it's going to need to talk to. And it will continue to pull the discovery service every 30 seconds and get updated addresses for all the other services that are registered. So this is how the big giant graph of services can register themselves as being available and healthy, and the consumers can then find the providers of a service, find out their addresses and where they are. In an environment where you don't do something like this, if you're not going to do DNS or you're not going to do discovery, like in our old model in the data center, typically these addresses would be provided by Chef at deployment time. So at that moment in time, you have to say, where is everybody right now? What are all their IP addresses? Put those in a config file, shove it on the disk, and then hope that they don't change very much while the machines are running. Or like rerun Chef convergence. Oh, thank you. Every so often to update. Like if machines are coming and going in clusters frequently, that's just not going to keep up. So discovery is dynamic. All of that state for what's alive and healthy right now at the moment is just kept in memory and discovery and updated continuously. And the other piece is that you might want to have some kind of runtime configuration that you would do in a Chef world where you say, I need to change some feature flag on this cluster right now because the feature is not being healthy. Let's turn it off right now. You would set some settings and run Chef to converge and tweak all those settings on the machine. In the Netflix model, there is a client-side library called Arceus, which incorporates properties from many different sources, and I have a picture later farther down about what that looks like in the Java side. But it can go out to a service or a database somewhere and grab a big pile of properties and bring them in. And it will do that on a periodic basis, so maybe every 30 seconds. Grab dynamic properties and sort of add them into the mix of the typical property stack. So you can have like feature flags that are pushed out into the service and managed that way. So we incorporated that technology into our stack. And you can see when you're doing a deployment here, you have the application AMIs, which are sort of pre-baked, and that's your app sitting on the machine, it's ready to go, but it doesn't have a lot of personality. We inject a little bit of config at deployment time with Asgard, which can mostly use to tell the app where it is. So, okay, you're being pushed in, EU West, and your purpose is you're going to be a beta cluster, and you need this personality. And then it will come up, find its neighbors and everybody it needs to talk to with Discovery, Eureka, and grab config, any kind of overrides for that moment, feature switches from using Arceus from the configuration server. So that way you have these different points where you can inject configuration into the application lifecycle without having to actually modify the instance that's running. Things that are fixed happen at bake time. Things that are dynamic can happen in these other two stages during deployment or runtime. And it's nice because then your machine image is immutable. You don't care about anything that's on the actual disk of any of the machines that you've pushed out. So that's kind of a key. So a little more detail about Eureka. So Eureka is the discovery service called Eureka is typically deployed as a cluster. You can have 2 or 3 machines. In the Netflix model, they like to always run in 3 availability zones per region. So they have like triple redundancy. And they'll run 1 Eureka per zone. And they all talk to each other. So there's a live, active standby in all 3 zones. All 3 are talking to each other. I should really have yellow dotted line here. But they're talking to each other and always syncing and coordinating with each other. So they all have the same snapshot of the world, same state of the world snapshot at any given time. Any of the machines that are publishing services or consuming services will talk to Eureka, either to post their own health and status to Eureka or to do a get and get back a big list of people to talk to, machines to talk to. And that's coordinated. There's also ways for the clients to sort of favor talking to services that are in their own zone if they care about that. So they'll try to talk to the Eureka that's closest to them, and if it's available, they'll talk to that one, and they can then choose and filter out services that are more local to it. But they can see everything, and if that one Eureka in their zone fails, they'll just fail over and talk to one of the other Eurekas. So it's a pretty robust service. And in the typical setup at Netflix, they would then run non-active standbys, well, fairly hot, warm standbys, I guess, behind each Eureka. So if the primary fails in a zone, the other standby will pick up and resync. It takes a little while, but it'll resync and then pick up from where that one left off. So almost never have outages in that case. And there's a number of features that Netflix figured out, things that can go wrong in the cloud that they dealt with through real life experiences. Like there was a number of cases where we had network partitioning issues in AWS where the networking between the zones broke. They couldn't see each other. And so from any one Eureka's point of view, it looked like half of the machines that they were talking to them just disappeared. So they would say, okay, they're gone, and just erase them from the state of the world storage that they had, sort of the split brain problem. But that sort of led to the case where so many would die, it would drop everybody from memory, and then when the network came back up, everybody would rush back in and just overload Eureka, and it would fall over, and so they ended up with this sort of vicious cycle of crashing and coming back up and down. So it has resilience built into it now that can deal with, if a lot of machines seem to disappear at once, it's probably a network problem, and it's probably not the machines. So it has this self-preservation mode that it will go into. So these are useful real-world solutions. So back down for configuration. The Arceus is the Java library that can help with configuration. And it's nice. It looks like annotations in the Java code. So you're annotating things as properties. So here's the property, here's its name, here's its default value. Where it comes from, where the value for that property comes from, can be a number of different places. And you can configure this stack of property sources. The default, very, very default is whatever you coded in as the default for the property itself. You can also have some standard values that are in property files that are part of your project that you just build and deploy and bake them into the AMI so that you have some sane defaults. If nothing's been overridden, it should at least do this in a normal way. Like how many threads are you going to run on your client thread pool, things like that. Okay, so that will have, when you do a push, you're able to add, in the Asgard user data, you can push and add different config files. So you can say, okay, we're going to override certain things. Here's a chunk of properties that we want to change when we push to this region or to this particular cluster. And then you have the dynamic properties that will pull in from an external URL source. So from the config server or from S3 or wherever, someplace that can be tweaked externally and managed with external config that will pull in to do things like feature flags and whatnot. At any point, too, you can query the app through a port and ask it, what is your current stack? What's the effective set of configuration properties that you're looking at right now? So what is the state? And where did everything come from? Now you have this switch. Which source did that switch come from? So that's pretty handy. But the way Netflix runs their property source, so they do their queries, they have a service that they haven't open sourced. I think it's pretty legacy, and they want to rewrite it, so they haven't open sourced it yet. And what they've included in the open source version of Arceus is a way to pull stuff from DynamoDB, which is okay. I mean, if you're doing small scale stuff, it'll work out of the box and it'll be easy to manage. But we wanted something a little bit more tailored to our case, and we wanted something maybe a little more high performance. We didn't necessarily want to go, we didn't want to be tied to AWS for this, because all these tools, I didn't really mention this, but all of these Java libraries are really about SOA, building good microservices. They're not tied to Amazon at all. So you could use these in the data center, and that's exactly what we're doing. So we wanted a solution for a configuration server that would work in our data center as well as in Amazon. So we came up with one which basically just is really easy to talk to from Arceus. So it does REST calls to query, get stuff. So we just say, well, what does that client-side API need? What kind of REST API are we going to write on the server? And then we just wrote it. And this is what we came up with. This is an example on the right. These little shots are from a JavaScript-based UI that sits on top of Swagger. So when we write our interfaces, we write basically a contract is a Java interface with annotations that describe what the REST interface looks like. And it will generate all the code for that and generate all the metadata for the Swagger. So then we can then pull up into the Swagger browser and look at what's going on and actually sit there and play with it. So you can make calls, you can do gets and puts and play around with the API through the browser. So it's pretty handy for learning somebody's API, or even your own, making sure your own API looks like what you thought it was going to look like. Anything else in there? Yeah, it's basically very fast because it aggregates all of the particular change sets in memory, so queries are fast. The clients will typically pull it every 30 seconds, say, this is who I am, this is where I am, what are my properties, and we'll get back sort of a resolved set of properties that are overridden for that particular application cluster. So all of those we've put together, so Arceus and various Netflix libraries, plus our own libraries, into a stack that looks kind of like this. I'll kind of walk through and break these down a bit. And this is evolving all the time. So we've had a number of teams that started out with, with Dropwizard. We wanted to build something that would be really easy to use for greenfield apps. And we integrated in the Netflix libraries, so we integrated in from the bottom. You know, we needed Arceus for configuration. We do Ribbon and Eureka client for service discovery and then load balancing across calls. So your client code will know where are the addresses of the services you're talking to and how to round robin between them. Hystrix is for circuit breaking. So if you're talking to a particular service and it's starting to fail, its guarantees and not coming back in time, you can circuit break and switch off and have an alternate provider for a particular piece of data or service that you need to call. You can pull stuff out of a local cache and then sort of delay having, so you don't pound on the service that's not working and you stop using it, stop waiting for it, and do an alternative for a little while. So we built this whole stack with Dropwizard and integrating Netflix into it, but at the same time we wanted to leverage our Hermes stack, which is a very simple low-level library that does the ambassador compliant REST APIs, client and server. So in the process of refactoring that a little bit so that we're leveraging more and more of Hermes extension. So one of the advantages of Dropwizard, it's really easy to use for new projects, but it's very opinionated, has its way of doing things. So trying to take a Dropwizard kind of model and a sort of an opinionated framework like that and apply it to an existing legacy application and try to retrofit that in there is really not feasible. So the Hermes libraries are very small, they're very easy to integrate, and so that's a really great solution for trying to retrofit and improve and break apart a monolithic app into small services. So we wanted the best of both. So what we ended up doing is pushing a lot of the Netflix integration down into these extensions for our low-level libraries. And then just putting Dropwizard on top as sort of a bundle, a bow wrapped around the whole thing, saying, yeah, you can have it all together in one big piece with Dropwizard, and we're doing that. So we'll be open sourcing these libraries over the next few months. So Hermes, we're just getting that ready, cleaned up and ready to go out for 1.0. And that integrates a number of the Netflix tools all together, Netflix libraries. So the next step, so phase 3, how do we get this all together? What does it look like all working together? So this is sort of the end-to-end picture in an AWS environment. This is basically just a combination of the other pieces where we have the bakery baking the machine, the images, either a base image or then the application images on top of the bases with some config and app bundles are being put on there. Applications come up in the cluster. They're pushed by Asgard with some more config at that time. Then dynamic config and addresses are resolved. And that all works in Amazon. But the picture in, So what we have there then is nice deployable artifacts for AWS. So we have AMIs. We can use those as a nice immutable deployable artifact. We have deployment tools for AWS. We have an SOA platform, infrastructure, libraries, everything for apps. And a nice set of libraries for different types of Java apps that we're building. And there are teams building things in C++ and in Go around the same APIs and REST interfaces and standards that we've developed. So we have this nice way of building SOA systems. But there's some limitations on where we are right now. So we have this deployable artifact is only for AWS and AMI. I mean, you can use it for Eucalyptus with just small conversions, but you're really kind of tied to Amazon. It's not universal. It'd be really nice to have a universal deployable thing. And it's kind of big. So the Amazon AMI machine image typically is about 10 gigabytes of a whole machine bundled up into a big tarball. It's kind of hard to pop into a repo and ship it around the world. So that's kind of a drawback. It's something you have to think about. And the deployment tool, Asgard, really relies on AWS APIs and infrastructure to do a lot of the heavy lifting. It's really kind of just a front end for it in a way. So these are challenges we still have to address. And some of the things we're looking at, like where are we going next, is we want to try to take care of those. So one of the areas we're researching now, looking into, is how do you solve the problem of this deployable unit, deployable artifact, I like to call it. We want a universal one. We want a deployable artifact we can use everywhere. So we've discovered, like many people, Docker, and this is a really great tool for bundling Linux images of application appliance type things. It could be anywhere from a single app to an entire machine image if you want, but typically it's quite small, and you can create these bundles and ship them around. They're small enough to be shipped around the world. You can deploy them on a cloud machine. You could deploy them on a data center machine. It could be on a private cloud in your data center. It could be on Metal in your data center. It doesn't really matter. It's just a Linux container. It works really well. We still don't have a solution yet, and we haven't figured out what we're going to do with the deployment on top of this, but there's a number of different technologies. The whole Docker space is heating up like crazy, and there's all these projects. And really the problem now is trying to figure out which are the ones that are going to be the most successful and which guys have the best architecture underneath. But there's a few that we're looking at. Fleet is from CoreOS, and it's part of the way it's built into the CoreOS set of distros. Quinn is another interesting project that's very young, but is purely Docker-oriented. Mesos has been around for a while, very solid, and now they have Docker support. So these are all different choices that we'll be looking into. And then in the same world, we have the Eureka and our version of Eureka and our version of the Arceus server. They work fine in this unified world. They're ready to go for cloud or data center. So those are really solid. It's just getting the universal container and getting the deployment tool. And then the big picture looks like that again, but you just have Docker instead of AWS. We can still bake Docker images. It's actually even easier than with Aminator. You just run Docker build, and you just have to be running on any Linux box, and you can bake with Docker. So we can just add that to our Jenkins workflow, and just have to figure out that deployer part. So that's what we got to do. So I have some slides and other talks that I've given before. If you're interested in, some of these are on the Netflix OSS, how the libraries fit together, things like that. So all the slides will be available afterwards. So that's it. Any questions? Yes, right there. Oh, we have the mic. Yeah. Oh, thanks. Hands up again. Yeah.
Check. Have you absolutely rolled out Asgard or changes to Asgard to support Docker?
No, I haven't actually. So that could be. That's why it's just question mark. So I mean, it could be that. And I know people have been playing with Asgard on different cloud platforms. And if Asgard ends up, it could be. Yes, so it could be.
How did you secure your REST web services?
We have a number of, I don't know if, I'm probably not the best expert on this area, but we do have a number, one of the plugins to the Hermes stack is authentication plugin. So we have a number of different types of auth depending on what team needs to do and what kind of auth information they have. So we can do basic auth and OAuth and things like that. So once the authentication is done, then it's HTTPS.
Why use Eureka and what was the configuration one?
Yeah.
Why use those instead of DNS and Zookeeper?
So it's interesting. One of the guys that worked at Netflix with us when I was there is a contributor to Zookeeper. He does the Curator project. And one of the things that was on their roadmap to do, and they did it, they did the work, is replace Eureka with Zookeeper. And they got it working, and then they realized that was not the right solution. Zookeeper is a really great tool for leader election and coordination of events, but its characteristics are different than Eureka. Eureka is really good at just keeping a big chunk of state in memory, serving it out really fast. And it's in an SOA world, it's just another SOA service. It's just, it's sort of the bootstrap one, so you have to be able to find it first. But once you find it, the way your apps talk to it is the same the way they talk to everything else, the way they talk to each other. So they're all at this REST HTTP layer, and it isn't a separate kind of protocol. So once you've tuned and you've got nice clients for making REST calls, it's just yet another one. And so it just made it easier to reason about the whole system when everything is just a REST call. Things like DNS, you have a lot of issues with caching and controlling the caching behavior on clients and timeouts, TTL, so that can be problematic. And Zookeeper, it didn't fit. The performance model and the failover model didn't fit what they wanted with that, so.
So when users logged on to Netflix, they may stay logged on for 3 to 6 hours if they are watching movies or something like that.
Right.
So in those cases, how do you push your code changes to those servers? Do you have any mechanism to transfer them to the different machines, or do you wait them to completely log off from their servers?
So in the Netflix, so when you're in the Netflix world, when you're watching the movie, you're not really you don't even need to be logged in. So most of the login, when you're interacting with Netflix service, is when you're browsing movies and deciding what to watch. So once you hit play, you're kind of off in the CDN world. But even then, your login information is really more of a token. So you've logged in, you've authenticated, you go back a token, your client has a token. You're not associated with any particular server at all anymore. So when you go back, every time you go back with the browser to hit the next page, or you're in your PS3 and you're hitting, the API calls, through the back end, that's going through ELB, load balancers, and then hitting a front-end API service or web front-end service. That's stateless. And there may be 100 of them, and you hit a different one every time. And it's sitting on top of other supporting services all the way down. Somewhere way in the back is Cassandra that's storing the data. We go one right over there.
With your current AMI model, to deploy a single line code change, like a JavaScript change, does that mean rebaking all the things?
It does. And that's the way, that's the first thing people will say. I just want to change one line of code. But do you want to one of the tendencies is I just want to change one line. I want to change a config file line, hack a little startup script. I'm going to just SSH onto the box and fix it, right? And you could do that to make sure that your change is right, but that change won't have gone through all of the whole testing life cycle of everything. And now you've created a snowflake. And when that autoscaling group autoscales, that machine's going to go away, and then a new one will come back later, and now all your changes are gone. So code changes should be done by rebaking in AMI, and really, if baking in AMI is painful, we should just do it more and more so we get better at it and get faster and faster at baking it. And the whole pipeline of code change through CI all the way to having the AMI ready, and then saying, oh yes, let's refresh my cluster with a new AMI, should be short as possible. But there's other ways of looking at it. That's why we have those two other points where you can inject configuration. So if all you want to do is make a code change or a config change, you could do that by repushing the AMI, same AMI out with a different config. Or if you have feature switches, feature toggles, you could do that with the dynamic configuration. So maybe if you're not sure about a feature, you got a new feature, you put that into flag controlled code and you switch it on and off at runtime. You do your A/B testing that way. But, yeah. Oh, the Netflix troll.
Yeah, no. I was really curious about Configurus because it looks like you solved a problem that we butt our heads against a lot. Is
Yeah.
So you have like fixed change sets of properties.
Yeah.
And is that to support like rollback of
Yes.
a collection of properties?
Yeah, so what we do is we post a change set, which is a collection of properties that are applied to a certain scope. So it could be, so I want to change the library config for all apps that are using this library. I want to change the default, let's say, cache size from this size to this size. Or it could be, I want to change one switch for this app in this region, in this environment over here, just change this one switch. So those sets are put together into a set. That set is committed to a database, but there's also a flag on whether the set is active or not. So if you push out the change in a chunk, so it'll be transactional in effect. So you might switch multiple features across different libraries and apps so they'd switch together. And then if you realize, oh, that something's wrong with it, let's roll it back, you could just go back and flip the state switch on that to roll it back. It will be, not yet, but we will be open sourcing all of that. Okay, I think we're out of time, so I'll be hanging around out there later on. So thank you.